All right, and welcome to the next lecture, which is on bipolar junction transistors. This is part one of two. Okay, so what is a transistor? So a transistor is a special part used in electronics, and it's made out of a material called semiconductor, which again is a material that can control electricity or current flow in some unique way. And so what it does, it has two main functions. First, it can amplify an electrical signal. It can make a small electrical signal much bigger, kind of like turning up the volume on a speaker. And then it can act as a switch, so it can turn electricity on and off in devices, just like a light switch. It's a three-terminal device, so transistors have three leads, three terminals, three connections instead of two. And these three terminals let it control how electricity flows in more complex ways than a simple diode, right, which is the two lead component. The types of transistors, we have several types of transistors. Some are listed here: BJT, FET, MOS, FET, MOSFET, CMOS, CMOS, and UJT. And I want to just spend a little bit of time giving you the highlights of each and what each stands for. But know that in this particular lecture and the next one, we will be focused on the first one, the BJT. And if you understand how that one works very well, you'll understand how the other ones work as well. So the first one listed here is a BJT, bipolar junction transistor. That's what we're going to be dealing with in this slide. And so what is this? It's a type of transistor that uses both electron and hole charge carriers to operate, just like our diodes. It works by having three layers: an emitter, something called a base, and something called a collector. So emitter, base, collector. Each lead is actually pertaining to one of those parts. And that's used for switching and amplifying signals. Again, these are just the highlights. We haven't seen them in circuits yet. And one key feature for BJT is that it relies both on types of electrons and holes as charge carriers for it to function. So it relies on both of those. The next one on the list is the field effect transistor. So what is this? It's a type of transistor that controls current using electric fields. So how does this work? It also has three terminals, but we call these a gate, a drain, and a source. And those operate by applying voltage to the gate to control the current flowing between the drain to the source. A key feature for the FET is that it uses an electric field to control the flow of current, and that makes it efficient for certain types of applications. MOSFET, you may have heard this name somewhere, right? It's metal oxide semiconductor field effect transistor. So it's a type of field effect transistor. This is the type of field effect transistor just that has an insulated gate. So it still has a gate, a drain and a source. The gate happens to be insulated. So again, three terminals: gate, drain, source. It uses this oxide layer to insulate a gate from the channel. And so what this does, it allows for high input impedance and very low power consumption. A key feature for the MOSFET is the gate that's insulated. Again, it just helps in high speed switching, low power consumption applications. The next one is CMOS, complementary metal oxide semiconductor. All right, what is this? Then you might have heard of the word CMOS. Right, so it's a technology used for constructing integrated circuits, including MOSFETs. And it works by having both an N-type and a P-type. Um, it uses the same N-type and P-type that you do in MOSFETs. So it's kind of a combination um, that helps create low power, high speed digital logic circuits. Right? So a key feature for CMOS is that they're energy efficient and they're widely used for digital devices or the type of material. The next one is a UJT. Sorry, getting word mix up here. Junction transistor, and this is a type of transistor with a single junction. And how does that work? Because it has three terminals. It has an emitter and it has two bases, a base one and a base two, and it's mainly used for triggering and timing applications. And so it's used in applications like pulse generation, timing circuits, because it's a very simple structure and it has very unique characteristics that allow it to do this. So, yeah, I just wanted to jump into those. And okay, the next thing on the slide is building block of electronics. Um, Fundamental building block of any electronic device. So, yeah, transistors are like building blocks of almost every electronic device, from your phone, computers. Without these transistors, modern electronics would not work. Watch the documentary on the history of the transistor to help you appreciate where we stand today with the technology that we have available. So going from something like a diode to a transistor, remember that PN junction diode? It has that two layers, the P-type, the N-type. So you add one more layer and you get something like a PNP or an NPN. And when you do this, you turn a diode into a transistor. And this can do a lot more than what a diode does. It can amplify and it can act as a switch. Let's keep going to the next slide. I'm going to keep going straight through. See if I can get this lecture done faster than the last one. All right, this slide. Let's go ahead and break this down into simpler parts. Transistor. We said what it was. Let's imagine a transistor, again, a special kind of switch or an amplifier for an electric signal. And it helps control the flow of electricity in electronic devices. That's what it does. It has charge carriers, all have these things charge carriers, but they're charge carriers for transistors. They work using those two main types of tiny particles called electrons and holes, excuse me. Electrons, again, just being the negative particle that moves around, it carries the electrical charge. And the holes are just those places, those spots, those storages, whatever you want to call them, where an electron, when an electron is missing, is where it moves to. So we say it carries a positive charge, right? So uh, in a transistor, you got both electrons and you got both holes, and that helps move electrical current, right? So you say, how does a hole help move electrical current? Well, you can't move an electron into a space that's already occupied. So by having holes, you create an opportunity for something to move. And so we call these bipolar transistors because it uses both types of charge carriers. They're current controlled devices. So think of a transistor as a gate that controls how much electricity flows through it. And the amount of electricity flowing through the transistor depends on a very small amount of current that controls the transistor. So we have, again, two types, PNP and NPN transistors. Transistor, again, we said had three layers. Had the P layer, N layer, P layer, or an N layer, P layer, N layer, right? So P and P transistors, the layers are arranged in that order, P and P. So the base is in the middle. So you know that the base in this case would be N-type. NPN, again, the materials are arranged in that arrangement. And so with an NPN, we know that the base is a P-type material, right? So I've been saying emitter, I've been saying base, hopefully I'm saying the right word, base, and then collector. What are these? So the emitter, that's the part that emits or sends out charge carriers. The base, this is the part that controls the flow of charge carriers between the emitter and the collector. And then the collectors, this is the part that collects the charge carriers after they've passed through the transistor. So these are two important junctions in a transistor, the emitter base junction and the collector base junction. The emitter base junction is where the emitter connects to the base, and the collector base junction, that's where the collector connects to the base. And again, it's all in reference to the base. Let's keep going. All right, continuing to break this down, let's go back to a PN junction, right? So what is a PN junction? It's again, that special part in the diode, but like in the same thing in the transistor, where two different types of materials meet, that P-type, which is the positive type, and the N-type, which is a negative type. And this creates that barrier or that junction between them, just like we did in the diode. Same thing's happening here when we're manufacturing these components. Which means we have something, we have a forward biasing component to get this thing to conduct. So to get current to flow through this junction, you need to forward bias it. And this just means that you need to apply a voltage that makes it easier for current to pass through it. So specifically for a PN junction, the base must be at least 0.7 volts higher than the emitter, just like it was in a standard rectifier diode. And then what happens when you apply 0.7 volts, right? When you apply this voltage to the base, the barrier at that junction becomes smaller, so it allows current to flow easier. And so electrons from the emitter, which is negative, starts to move toward the base, which is positive. Again, we mentioned electrons and holes as carriers. A little more expansion on that. Electrons, particles that carry negative charge, move from emitter to the base. And holes, right? These are like the empty spots, the areas where the electrons occupy. And we say they carry a positive charge or a less negative charge. So that's why the electrons will move toward them to begin with. Remember, we had recombination with the diode. We also have recombination here in the formation of these junctions within the transistor, recombination and in current flow. So when electrons from the emitter reach the base, they mix with the holes in the base. Sorry, my hands are sore. I'm doing this. If you can see my, yeah. Okay, what is that? Yeah, recombination. I don't know, my hands are sore. And what else? So the base is very thin here, and there aren't many holes, so the base current is actually very, very small. And you'll see this when we do the calculations, that you have a tiny, tiny base current. So when you get something extremely small in base current, it's normal. What happens to the holes? So some of the holes in the base, they'll get pushed back into that emitter region, and that's because the way the voltage is applied and how the transistor is designed. Okay, let us go to, I think I'm making good time. Did it move? No, it's not moving. Why not? There it goes. All right, let's continue with reverse biasing the base collector junction, right? So transistors now. Remember, so we're talking about transistors. We got two PN junctions, or two junctions, right? PN and PN. And so you have two important junctions: base emitter, base collector. And so when we talk about reverse biasing the base collector junction, it means applying a voltage in a way that it makes it harder for current to flow between the base to collector. So reverse biasing, what does that do? So within the collector region, this is where you apply a small positive voltage. The positive voltage attracts electrons from the base region and it pulls them into the collector. Um, and then that causes a movement of electrons. Electrons that are in the base regions are attracted to the positive voltage in the collector region. And this movement of the electrons across that reverse bias junction, base collector, that results in a current, right? So we have current amplification. So you have a small current that flows through the base because of the applied voltage on the base, and that leads to a much larger current flow through the collector. So this is uh, due to the way the transistor is designed and how the reverse bias affects the flow of electrons. So small current signal in the base, larger proportional current flow from the collector to emitter. Right? All right, let's go down even further on this slide. So we're going to continue breaking this down. The resistance and electrons. So where is this resistance coming from? Think of resistance as how hard it is for current to flow through a part of the circuit. So low resistance just means it's easier for current to flow. So give me a second. So when you have more electrons, that means that resistance is low. Electrons gather in the emitter region of the transistor. Um, there's an attraction by the collector voltage. So the collector voltage has a positive charge that you're applying to it. We also call it VCE. You'll see that on the schematics. You have a VCE up on top, voltage collector to emitter. And this positive voltage attracts the electrons from the emitter through the base and into the collector. So all of this to increase current flow to create current amplification. So because the emitter has lots of electrons and the collector pulls these electrons strongly, the current flow through the collector, which is the output current, that's much larger than the current coming into the base. So base a tiny, tiny current, which is the input, and then a large output current on the collector because of this. So, and that's where we get our current amplification. So, and it being proportional, we can replicate a tiny signal into something much larger. Oh, Okay. There we go. There's our circuit. So here's a a circuit that just displays a transistor with a V2 being the small voltage being applied on the collector, and then a 0.6 volts being applied to the base there. And you can see you have hardly any current flow. You have 0.77. I'm trying to look at the schematic with the corner of my eye over here. 0.77 microamps, so something super negligible. And then up on the collector is 0.08 milliamps on the collector. All right, going. Um, okay, and so in this case, we're just increasing the voltage on the base from 0.6 to 0.7. Notice that the base current actually jumped up from that nano to 0.24 milliamps. And then we got something significant as far as a transistor is concerned, 3.6 milliamps. So you get something much larger there. I know milli might not seem like a much, but it is significant compared to 240 microamps, basically. All right, and here we go. We're increasing that base voltage even higher, past that 0.7 volts. So once we go past that 0.7 volts, we forward bias the base to emitter. I don't know if you can see. Hopefully you can see this. Can you see the mouse? You cannot see the. Hold on, let me do the laser pointer. Ah, there we go. Okay, so that's the base, that's the emitter, and the collector's up here on top. So yeah, you weren't able to see the mouse. I was pointing to stuff and I don't think you could see it. But look at now, we have this 0.8 volt being applied to the base. Notice that the current is 0.6 milliamps or 608 microamps. It's still going to be something in that range. So 608 microamps may be small, but not according to the base. That's all it's requiring. It just needs that about that much. And then what do we have on the collector? 0.07 amps or 70 milliamps. All right. Okay. Another multi-sim circuit. Here we go all the way up to 1 volt on the base. We're keeping 1 volt on the collector. Notice that we actually get a pretty significant current on the base. We have 1, 2, 3, 12 milliamps now. That's much higher than that 700 nanoamps that we started off with at the very first slide. And then we have 0.46 1 amps or 461 milliamps going to the collector. So we're moving this up where the collector current is getting higher and higher and higher. But there's going to be a limit to it, right? There's going to be something called the saturation current, meaning the current can't go any higher than this as I'm increasing the voltage on the base. And then here we see the current going through the emitter. So here we go. That's the emitter, 0.473 amps or 473 milliamps, 0.461 amps or 461 milliamps, and then 0.012 amps or 12 milliamps on the base. 12 milliamps, and then 0.461 and 0.473. Just to let you know, right? So 473 should be equal to, like down here, the current in the emitter. This is Kirchhoff's current law. The input current must equal the two branching currents, IC plus IB. So 473 should equal to this 0.012 plus this 0.416. Right? And to simplify things, always know that the emitter current, which is definitely down here, and the collector current, they're going to be very close, almost the same. So if you needed to do some kind of quick calculation just to get an approximation, you know that these two need to be, when it's conducting, they need to be almost the same thing. So we do that in shortcuts once in a while just to uh, get an idea of what to expect instead of running through these whole calculations. What side am I on now? Wow. Okay. What do we got here? Transistor currents. So this just is just showing transistor currents, right? So we have this is the NPN type of transistor, and that's a schematic that it looks like. I'm sorry, I need to blow up my schematic so I can see it. There it is. Okay. The camera's here. slides right there, but I have a blow up of it here. So y'all know what I'm looking at. And where is my thing? There it is. So this is a schematic of a transistor. Specifically, this is an NPN transistor. So NPN, and the schematic symbol for an NPN looks like this. You see that little leg there with the arrow pointing out? That tells me that this is an NPN transistor. A good way to remember this is if you reference it toward the arrow, not pointing in, NPN. That's what I was told, 40, 50 years ago. And yeah, so that's a nice way of remembering it. NPN, not pointing in, meaning the arrow's pointing out. So that is what it would look like if it's NPN. And if it's a PNP transistor, it's just that the arrow's pointing in. So PNP, pointing in, I don't know. If you remember NPN, then you know that PNP is pointing the other way. So if you see a symbol like this, you know that you have to have, you're going to have higher current on the emitter, higher electrons, and then more holes in the base and the collector. All right, I know that everything here is showing conventional current flow going from plus to minus, but also remember that electrons are flowing in the opposite direction. If you do the math equations, it's going to work out the same either way, as long as you're consistent and use one convention. All right, so it says emitter current IE is the sum of the collector current IC and the base current IB. So, all right. Okay. Let's talk about biasing, right, in a transistor. Excuse me. We mentioned biasing with diodes of that. What do you need to get it to operate? So when we say biasing in a transistor, this means setting up voltages in a specific way that makes the transistor work correctly. And I've done a tutorial video on how to calculate a basic BJT bipolar junction transistor circuit. And then you just follow that tutorial, and that'll help you. Why is my laser pointer still in the center? Okay, there it goes. All right. We have VBB, which is the forward biasing. VBB is the voltage that's applied to the base of the transistor. You can apply it directly, or you can apply it through a voltage divider. Forward biasing the base to emitter junction, and that just means that it makes it easier, again, for current to flow from the emitter to the base. Hold on. I gotta center myself in the camera. All right, I'm trying to look at myself. There we go. I think right there. I'm always leaning and sliding, going out of frame. All right, so VBB is forward biasing as it pertains to the base. BCC and reverse biasing. Remember, we reverse bias from the collector to the base. So this is the voltage that's applied to the collector of the transistor, and it reverse biases the base collector junction, and that just means it makes it hard for current to flow between the base and collector. We also have some factors called the DC current gain, or beta, right? And this is a measure of how much the transistor can amplify current. So it's the ratio of the current flowing through the collector, which is I sub C, to the current flowing into the base, which is I sub B. So if the collector current is much larger than the base current, the transistor has a high current gain. So the beta would be equal to I sub C divided by I sub B. Again, this is DC current gain. When we talk about alpha current gain, so alpha is just another measure of current gain, and it compares the collector current I sub C to the emitter current I sub E. So alpha shows how efficiently the transistor converts the emitter current into collector current. So alpha alpha sub DC, right, is equal to I sub C divided by I sub E. Did I say that correctly? Alpha sub DC is equal to I sub C divided by I sub E. Okay. Alpha sub DC. Okay, it just sounds weird. Yeah, let's keep going. All right, we're making good time on this one. All right, so let's see if I can zoom this circuit in so I can see it a little better. There we go. BJT circuit analysis. I'm going to go ahead and talk about this, but I'm going to show you a video that's going to give you, it's going to give it to you in more detail, more steps. So that's when the base emitter junction forward bias is forward bias, voltage base to emitter is 0.7 volts. So it's saying the voltage across this section right there because it's 0.7 volts to overcome that voltage. You have to apply 0.7 volts in the opposite direction to balance that out so that current can start flowing. That's all it means. So you have to forward bias it for it to conduct. So the voltage on the base is equal to the voltage on the resistor at the base, which is this one, plus the voltage base to emitter. So you do a KVL right here, and you come up with that formula. You solve for voltage at RB, what the voltage drop is there, and that's going to equal to VBB minus VBE. VBE is 0.7 volts. And so that's going to let you know what you need to design the circuit for to give you that voltage so that it starts conducting the minute you add a signal, right? So when we're talking about DC bias, when we're talking about biasing, sometimes called DC biasing, we're designing the circuit just with the DC voltages to get it to be ready to conduct, right? We haven't added a signal yet, so this is way before we even add signals. Right? And then using Ohm's law, we get if we want to define the current through the base, IB is equal to VBB minus VBE divided by RB. All right. I know the KVL. This one is through VCC, through IC, through the IE, right? Collector to emitter. So VCC is equal to the voltage across the the collective resistor right here, plus VCE, meaning the voltage that's being dropped across this component, across the transistor. Right? So VCE is equal to VCC by rearranging this minus IC times RC. So IC times RC is just the voltage being dropped across that resistor. Ohm's law. Right? So yeah, it just tells you here, Ohm's law, VRC is equal to IC times RC. So all they're doing is substituting up here. And then remember that IC is also equal to beta DC times IB. So beta, you can always get it from the spec sheet. And so that's one way of doing it. But if you don't have this and you're just doing this like on a textbook problem, and they're not telling you exactly what transistor you're looking at, you can calculate it. So IC is equal to beta times IB. So once you find IB, you can find IC. Once you find IC, you can calculate VRC, and then you can find VCB, which is equal to VCE minus VBE. All right. Ooh, last slide already. All right, so here's an example. Determine current to the base, current to the collector, current to the emitter, right? IB, IC, IE. And then voltage across the base to emitter, voltage across the collector to emitter, and the voltage across the collector to base. The transistor has a beta DC of 133. I think it's going to, yes, it does. Fantastic. Yeah, so we can use the formulas we know already. IB is equal to VBE minus VBE over RB. We just kind of plug and chug from the numbers we have here on the schematic, and we end up with 430 microamps, and that's fine. That's about right for base current. It will be tiny, 0.43 milliamps or 430 microamps, and that's like a normal range. If you had something like 1 milliamp, 2 milliamp, 3 milliamp, anything like that on the base, you've done something wrong with your calculations. Because that takes a tiny, tiny amount of current. It doesn't need that much. Anything like that would be too much current. The collector current, on the other hand, you're going to have something in milliamps for the collector current. So you can calculate it by beta times the base current. This BDC up here, this is from the spec sheet. So it's either going to be given to you on the problem, or if they somehow just give you the part number of the transistor and they don't give you a beta, you can Google it, look it up, find the spec sheet, and then get the beta for that transistor. Right? But then you can find collector current this way. We know what emitter current is using Kirchhoff's current law. We end up with this. Now notice that emitter current and collector current are very, very close. They are always going to be very, very close when it's conducting. If you get something that's really far off, either the thing is not designed to be biased correctly to be what do you call it, operating, or you did something wrong in your calculations. So if IC was like 42 milliamps and IE was like 57 milliamps, you've done something wrong in the calculations. They should be extremely, extremely close. The difference should be the I sub B, right? 430 microamps between these two. And then VBE, because of the type of transistor and the material, it's silicon, 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 silicon. diode. I keep saying silicon. That's already set by manufacturing, so it's set to be around 0.7 volts. Now, you've learned with your diode labs that it isn't actually 0.7. It could be like 0.69 something. It's going to be something not exactly 0.7. For calculations, just do 0.7 to simplify it, right? And that's going to be another place where you might have some inherent error because of your calculations. And then you just plug this into the formula. VCE is equal to VCC minus the voltage on the collector resistor. We end up with 4.29 volts. And that's off a 10 volt DC source on that collector right there. And then voltage from the collector to the base from here to here, just that drop across that is VCE minus VBE, which we end up with 3.59 volts. And I think that's all it's asking. VBE, VCE, VCB. VBE, you don't have to calculate because that's just the manufacturer at 0.7 volts. Base to emitter. Right. Okay. And that's it for this lecture. Thank you very much, and I will see you in part 2 of bipolar junction transistor.